I am a physicist. I have spent 10 years wielding chalk, staring at blackboards, and feeling them stare back at my soul. My job is to understand the laws of nature. Thus, I write. I write down formulas to describe how spacetime bends when energy piles up. This should be the most exciting story ever written. Yet, I feel nothing. I beg for meaning and receive silence. Why does the deepest of all mysteries fail to touch my heart? After all, these are no more than modern answers to ancient questions around which people constructed their identities, values, and nations. Cosmology far precedes Einstein and Hubble. Perhaps it is in people that I'll find what I'm looking for. I can't fill my formulas with meaning, reveal their true colors, without moving away from the blackboard. I'll embark on a journey to trace the human roots of cosmology, and there's no better place to start than an island where nature speaks first through volcanoes and geysers. Today, I'm going to Iceland.
The year is 868. Floki Fylkerþarsson leaves the Scandinavian shores and sets sail for an almost legendary land in the far north. After exploring the western coast of modern-day Iceland and settling in a fjord, he's said to have experienced such a harsh winter that he came to believe this place was not meant for humans. His story is told in the Landnama Bok, one of the many Nordic medieval writings collecting historical accounts, family trees, and mythological tales. One cannot understand what these people thought about the universe, what their cosmology was, without engaging with this enormous literary corpus. This is something I could have never done by myself. Fortunately, I found some help.
When we refer to Norse mythology, we are mostly using texts that were written in Iceland in the 13th century by totally Christian writers who didn't believe or practice in any pagan rituals, the myths that must be behind the mythological stories and poems that we have in the books. So we have to try to think of what was the cultural context for this material in the Christian culture in Iceland in the 13th century. But we can also see from place names and picture material and various bits and pieces in other writings that the ideas, the characters of these stories and poems written down in Iceland must have been shared by the people of the north, even in the Germanic language area. So we can talk about the shared mythology of the Germanic cultures, but with a very Icelandic 13th century twist.
Most of what we know about Norse cosmology we owe to Snorri Sturluson, an Icelandic historian and poet, as well as a relevant political figure who lived between the 12th and the 13th centuries. Among his best-known works is the Prose Edda, in which he collected and systematized the whole universe of Norse mythology. At the heart of the poem is the unbridgeable difference between gods and mortals. It is then quite remarkable that the first Edda book starts precisely with a dialogue between creatures belonging to those two distinct realms.
He sets it up as a dialogue between a Swedish king and the divine trinity that he meets, who start explaining to him the world as he sees it with his bare eyes. That what he sees is not really what it appears to be, but they explain it through stories as being a mythological phenomenon. So that is the illusion in the first part of the Snorri's textbook, the Edda, which is referred to as Gylfi's illusion, because he's made to see a totally different world from what it appears at first to his human eyes.
Here, close to where Snorri used to take his thermal baths, one can almost hear the echoes of ancient stories. Stories about a primordial void, otherworldly forces, and giants dismembered to assemble the world.
The myths in Snorri's time, they also have their idea about how the world came about, how everything was created from nothing somehow. And in order to express that moment, they think of the extreme forces that they know of, the extreme heat, the extreme cold, and they somehow meet in the void that was in the beginning of time, and somehow their meeting creates matter and material that everything gradually can be made of. And the world here, our sort of Earth where we humans live, is the result of a giant being killed. So his bones and flesh and blood are used to create the Earth, and the sky above us is really a giant skull.
It is hard to imagine how some of our ancestors, more or less 1,000 years ago, would have walked here, looked at the sky, and identified it with Ymira's skull. These ideas strike us as alien, unthinkable, too distant to truly believe that someone would ever grant them the same status we now attribute to our scientific models. The mistake we make in this is to assume we can engage with fragments of a belief system without truly experiencing it in its cultural context.
I think in general, when we think about myths and mythology in our modern culture, we think of lies and imaginary ideas and so on. But where myths are part of a living culture, they are really a scientific way of thinking about the world we live in, containing and mediating analysis of human behavior, and not least the physical world we live in, as we see it with our bare eyes. And we must try to rewind back before our notions about the solar system that we have become so accustomed to, thinking about the world as a three-dimensional phenomena that we can observe from the outside, but start looking at it from the phenomenological perspective of the people living down here on Earth, and what they see, how they experience the world, the sky, the earth, and the lands beyond. And this they deal with, this they explain to themselves and to others around them with mythological terminology.
In the end, physics too speaks of a word coming from a single, dense entity. Black holes and neutron stars, galaxies and solar systems, all emerged from some sort of cosmological Ymir. I guess it's now time to chat with those people whose job is to precisely understand how all these things actually came into being.
A definition of cosmology, well, I mean, literally, I guess it comes from the Greek, logos being the word or a study of, as in like theology, and cosmos, in some sense, everything, the world, universe around us. In the modern sense, we understand it to mean a study of the universe in its entirety. And so in modern physics, we distinguish between astronomy, which is more of a local study and looking at the stars, and cosmology, which is really understanding the universe as a whole. So we want to understand, ideally, where it came from, how it evolved, and how we are where we are today.
People once believed space and time to be distinct and static, forming some sort of background for physical processes. It took a while for us to understand that they were actually part of a single object we now call spacetime, and that such object was itself physical. Space-time bends, twists, deforms whenever matter is present. Our best description of this phenomenon is the one offered by the general theory of relativity, which then becomes a natural setting for studying how our universe evolved.
There's evidence that the universe has changed over time in a rather interesting way. That today, as far as we know, the universe could be infinite, that you go as far as you want in any direction. There's galaxy after galaxy that way, and galaxies that way, and that way, and that way. We're just embedded. Our galaxy is in a sea of galaxies that goes on forever in all directions. And that's our current best picture that we can, as far as we can see. But what we started realizing is that as you look further away, you're looking further back in time because light took time to reach us. And everywhere you look further and further back in time, the universe was more dense. It's as if all of the space between all these galaxies has been slowly sucked out and it's disappearing, and everything is closer and closer and closer to each other. So it could still be infinite as far as we know. So just, as many galaxies in all directions as there ever were, it's just that there's not as much space between them. They're all closer to each other.
Our universe began as a hot, dense entity, which then expanded and cooled down with galaxies forming and moving away from each other. Bear in mind, though, this is not just about stuff traveling within space. It is about space itself getting bigger.
When we say that space itself is expanding, it's very hard for our brains to figure out how to deal with that, because things that are tied together, like the chair and our bodies, there are many things that keep them attached. And so in a universe that's expanding, they still look the same. They still look like a chair, but anything that's not bound together like that will have its distance from the other things get bigger. And so if we have no gravitational attraction between us, we would just be getting tiny bit further apart. It's apart in a billion, in any time frame that we would watch. And so we can't even we would never see it. But when you work in astronomy, you're looking at huge time spans. When you look at very distant galaxies, you're seeing galaxies that are 1 billion light years away, 3 billion light years away, 7 billion. So that means that you're actually allowing enough time to have passed that the universe has expanded significantly.
Physics is an empirical science. Any claim requires evidence. To check whether nature agrees with our expansion models, we mostly observe electromagnetic radiation, the kind of stuff light is made of. That's why we look for standard candles, namely for stable and reliable sources of light.
All the Type 1a supernovae have very similar patterns. They brighten to about the same brightness and then they fade away. Now, that's really useful because if you know that you have an object that's always the same brightness, now you can use it as a standard candle, we call it. You can tell how far away it really is based on how faint it looks to you. And so the further away it is, the fainter it looks. And so you just can measure how bright the thing is, and it tells you how far away it is. And also, because we know that it takes time for light to travel at the speed of light, we know that for a explosion that is that far away, we must be seeing something that happened along this time back in history.
We observe supernovas, estimate their age by how faint they appear, and mark points in time. To infer the actual rate of expansion of the universe, though, we need to precisely measure how much space stretched between those points.
There, you're very lucky because since you know what the supernova really looks like when it's close up, you know that it's mostly blue light that you see. That's a short wavelength of light. Turns out the wavelengths of light they're not nailed down. They stretch when the universe stretches. So while the light is traveling to us, it begins looking blue, but by the time it reaches us, it's been stretched redder and redder and redder. And you can just read off from how red it gets, how much the universe must have stretched since that time.
Given the attractive character of gravity, a natural expectation would be for the expansion to slow down, stop, and eventually lead to a cosmic collapse. When Professor Permutter and his team tried to figure out whether this was indeed the case, they ended up being quite surprised.
You can actually make a graph of how much the universe stretched at each time back in history, and we just looked at the graph and looked to see how much that stretch has been slowing down. And of course, when we looked at the graph, it wasn't slowing down; it was actually speeding up. And that was the surprise. We assumed, by the way, that something must have been wrong with our measurement, and so we spent probably 9 months looking for all the possible ways that there could be a mistake in the measurement. And eventually, after we did all the tests that we could think of, we decided we had to start showing the other scientists what we were seeing.
Our universe expands, and it does so ever more rapidly. This discovery won Professor Perlmutter, along with Professors Brian Schmidt and Adam Riess, the 2011 Nobel Prize in Physics. Still, we have no idea what kind of engine drives this accelerated process. We have yet to crack the mystery of dark energy.
From a more foundational perspective, what is this dark energy? It is very, very small. Our universe is very cold now, just below 3 Kelvin, and very empty. And so if the dark energy is only just now making its presence felt, that means it has to be very, very weak. And the problem with that is it's really quite hard from a quantum perspective to explain that. So when you have a very, very small number, first of all, it's difficult to explain why is it so small, but in the end, maybe you just decide, okay, it is what it is, I'm not going to argue. But then what we know from our experience in quantum field theory is that the way in which we observe something can actually often change its nature. And so when we try to sort of pin down why this constant is so small, it is incredibly hard to achieve within our knowledge, if you like, of quantum physics.
Here is where my first journey must end. There are too many seas yet to explore, too many stories to hear. I need to go further. Before moving on, however, I have to go back home. I'll mix the treasures I've collected with my formulas, sculpt this dialogue with chalk and sweat. Only then will I take a first step towards a true cosmology in colors.